Imagine pulling up to a charging station, plugging in, and watching your battery jump from 0 to 80% in exactly 4.5 minutes. By the time you've bought a coffee, your car is ready for another 300 miles. That is the ultimate promise of solid-state batteries. And recently, a highly publicized lab test claimed to have finally cracked the code. But there's a massive catch that everyone is arguing about. During that blistering fast charge, the single test cell quietly climbed to a scorching 90 degrees Celsius. So what does that heat actually mean? Is it a fatal flaw that proves solid-state batteries are still decades away from reality? Or is it just a misunderstood data point from a stress test pushed to the absolute limit? If you scale that 90-degree cell into a massive, tightly packed electric vehicle battery sitting under your floorboards on a blazing summer day, do you have a revolution or do you have a thermal nightmare? Let's break down exactly what this 90-degree threshold really tells us about the future of EVs, and more importantly, what it doesn't. To understand the debate, we have to look at the raw numbers from the independent test results out of the VTT Technical Research Center of Finland. On paper, the headline is nothing short of spectacular. A solid-state cell was pushed to an extreme 11C charge rate. To put that into perspective, an 11C rate scaled up to a full-size vehicle pack would imply well over a megawatt of continuous charging power. Under those punishing conditions, the cell skyrocketed from a dead zero to an 80% state of charge in just 4.5 minutes. For some much-needed context, most production lithium-ion electric vehicles on the road today handle fast charging somewhere between 2C and 4C. Only the absolute most aggressive, cutting-edge systems briefly touch 5C or 6C, and that is only under perfectly ideal preconditioned temperatures. So 11C is not normal fast charging, it is absolute stress test territory. But alongside that record-breaking speed came the number that ignited a massive debate across the industry: the temperature. During the charging cycle, the surface temperature of this single isolated cell rose from a comfortable room temperature of 26 degrees Celsius to 63 degrees Celsius while using 2 heat sinks. But when the engineers removed one heat sink, limiting the passive cooling, the temperature kept climbing, eventually hitting that magic number, 90 degrees Celsius. At that exact moment, the laboratory aborted the test for safety reasons. And that single moment, that 90-degree peak, is where the entire narrative splits into two completely different camps. On one side of the argument, you have the pack engineers and industry skeptics who look at that 90-degree figure and immediately see a massive red flag. Their concern isn't necessarily that the cell itself failed, but rather what that amount of heat implies when you zoom out from one tiny, isolated laboratory component to a full-scale electric vehicle. Their reasoning is highly practical and rooted strictly in the brutal realities of pack engineering, not just battery chemistry. Think about it. A single cell sitting in a climate-controlled testing chamber strapped to direct heat sinks with carefully managed airflow is experiencing the easiest, most forgiving thermal environment it will ever see in its lifetime. Real-world cars are the exact opposite. In a real 60 to 80 kilowatt-hour battery pack, hundreds or even thousands of individual cells are packed incredibly tightly together into a sealed metal box. Every single cell is generating heat, actively warming its neighbors. Airflow is virtually non-existent between the cells. You have added heat radiating from the bus bars, the high-voltage contactors, and the power electronics, all while the car might be driving over black asphalt in 45-degree ambient summer temperatures. So the skeptic's concern isn't that the solid-state cell can't survive the heat, it's that controlling that behavior at the pack level would almost certainly require incredibly aggressive thermal management. We're talking about heavy-duty liquid cooling loops, massive high-flow pumps, thick cooling channels, and extra insulative materials. All of that means more complexity, significantly more weight, and drastically higher manufacturing costs. And every single one of those additions eats directly into the very advantages that solid-state technology is supposed to offer in the first place: absolute simplicity, record-breaking energy density, and ultimate price competitiveness. If you have to wrap your super light solid-state battery in 100 kilograms of liquid cooling gear just to stop it from melting down during a fast charge, have you really moved the needle forward? It's a compelling argument, but it's only half the story. Because if you look at how material scientists and battery chemists interpret that exact same test data, the tone shifts completely. They push back with a fundamentally different interpretation of the data, pointing out a crucial detail. The test wasn't stopped because the battery degraded, it wasn't stopped because it short-circuited, and it certainly wasn't stopped because it went into thermal runaway. The test was stopped entirely because of standard laboratory safety protocols. Testing facilities have strict, predefined temperature limits for their equipment and testing chambers. Once the cell hit 90 degrees Celsius, the technicians simply followed standard operating procedure and cut the power. From a chemist's point of view, that number doesn't represent a hard chemical failure limit of the solid-state battery at all. It just represents the line where the lab chose to say that they had gathered enough data for the day. And technically, they are absolutely right. Industrial cells, heavy power electronics, and many high-current components are designed to tolerate short periods at highly elevated temperatures without sustaining immediate catastrophic damage. When you push massive amounts of electrical current through a highly compact system, you get resistive heating. It's an unavoidable phenomenon known as Joule heating. It's just basic, undeniable physics. At an 11C charge rate, you are forcing an absolutely enormous amount of current through a highly compact system. Of course it gets hot. Arguably, anything would get hot. Therefore, this camp argues that hitting 90 degrees isn't evidence of a fatal design flaw. It's simply what naturally happens when you stress any electrochemical system this aggressively. To them, using that specific lab temperature as definitive proof that pack-level charging is unfeasible feels entirely premature. The data only proves that the cell generates heat under an 11C load. It doesn't prove that a properly engineered pack, equipped with modern, active cooling plates, couldn't easily manage and dissipate that heat. And this is where the debate gets truly fascinating. If both sides are looking at the exact same 90-degree metric, why do their conclusions sound like they are talking about two completely different technologies? The number is the same, but the reference frame is entirely different. In a laboratory environment, temperature is often pushed intentionally. Engineers deliberately drive small prototype cells with massive, aggressive current loads specifically to find their failure limits. They aren't trying to simulate your daily commute to the grocery store. A prototype test cell might only hold a tiny amount of energy, maybe 1 to 5 amp hours. When you slam a cell that small with extremely high current, it heats up incredibly fast, simply because it possesses very little physical mass to absorb and distribute that thermal energy. That rapid temperature spike doesn't automatically equal danger. It simply means the cell is being stressed well beyond normal, everyday operating conditions to expose its microscopic weaknesses. It's remarkably similar to strapping a brand new car engine to a dynamometer and revving it to the absolute red line until the exhaust manifolds glow bright red. Nobody actually commutes at that RPM. Nobody drives like that in the real world. But as an engineer, you absolutely still want to know exactly where that mechanical limit is. From that laboratory perspective, hitting 90 degrees without a catastrophic failure is actually a massive victory. The cell didn't burst into flames. It didn't short out internally. It didn't show immediate thermal runaway.
For a material scientist developing cutting-edge solid-state technology, that looks like incredible progress. It strongly suggests that the solid electrolyte and the internal structure remain highly stable even when pushed to the absolute brink. But the moment you move from that single victorious test cell to a full vehicle pack, the physics shifts in ways that are dangerously easy to underestimate. A real-world electric vehicle is not a single prototype sitting on a bench. It's an intricate ecosystem of hundreds or thousands of cells working together inside a tightly packaged, highly insulated structural box. Take a look at the architecture of something like a modern mid-size electric crossover. A typical version carries around 75 kilowatt-hours of energy storage and relies on hundreds of kilograms of battery mass. That monumental amount of energy isn't concentrated in one giant unit. It's distributed across complex modules filled with many cells packed mere millimeters apart. 90 degrees Celsius.
Yet pioneer companies pushed forward anyway. Early vehicles utilized thousands of tiny, small form-factor cylindrical cells packed tightly together. Industry critics were ruthless. They called the design overly risky, needlessly complex, and a massive fire hazard just waiting to happen. And to be completely fair to those early critics, those first-generation packs did run hot. They did require incredibly heavy, over-engineered liquid cooling systems. The engineering wasn't elegant, it certainly wasn't cheap to manufacture, and it definitely wasn't optimized for mass production. But over time, relentless engineering closed the gap. Chemists developed better, more stable cell chemistries. Software engineers built vastly smarter, predictive battery management systems. Designers created highly precise, micro-extruded cooling plates. And tighter software control loops gradually, year by year, pushed those operating temperatures down and pushed the overall reliability up. What looked terrifyingly fragile at first eventually became boringly stable. Today, millions upon millions of lithium-ion packs operate daily in extreme climates all over the world without a hint of drama. The exact same fundamental chemistry that once terrified investors now powers everything from compact budget sedans to massive electric delivery vans. We saw this exact same transition happen even more recently. Look at the rise of LFP, or lithium iron phosphate chemistry. For years, LFP was entirely dismissed by industry analysts. They claimed it had terribly low energy density, poor cold weather performance, and was strictly only suitable for heavy city buses or extremely low-range utility vehicles. The consensus was that LFP could never, ever compete with the energy-dense, nickel-rich chemistries dominating the market. Fast forward to today, and LFP is widely used in entry-level and mid-range vehicles globally because the industry figured out how to package it. It turned out to be drastically cheaper to produce, inherently safer regarding thermal runaway, and heavily outlasts traditional chemistries. Modern vehicles running LFP packs routinely exceed 3,000 full charge cycles with minimal degradation. The lesson here is incredibly simple, but it is deeply important when looking at the future of solid-state technology. Early laboratory numbers almost always look vastly worse than the final polished consumer products. High temperatures, awkward physical constraints, heavy cooling requirements, and strange performance limitations are entirely normal during the experimental, bleeding-edge stage of development. Material scientists and engineers intentionally push these cells to absolute extremes because pushing the extremes is the only way you find the edges of what the technology can actually do. This current debate over a 90-degree fast charging cell isn't a fight between skeptics being completely wrong or optimists being completely right. It is simply a difference in the lens through which we view innovation. One lens looks at the immediate engineering hurdles of today, while the other looks at the chemical potential of tomorrow. So the ultimate question remains, if a revolutionary new battery technology can charge insanely fast but runs significantly hotter in early prototype testing, would you still trust the engineering process enough to put it in your next car? Do you care more about the raw, extreme performance in the laboratory, or does your confidence rely entirely on the long-term reliability and cost-effectiveness of the final product on the showroom floor?